Okay, I've started to fill this out. I've already drawn the normal force and gravity in every picture because we know they're always there. This question says friction is present. The block is going up the ramp, so friction opposes that. Now, we want to draw the applied force because they do say there's an applied force for this one. So let me add that to my picture. The applied force, they say, is directed up the ramp. Okay, the applied force is something like this, maybe. The applied force will always be parallel to the ramp in these problems. We also have to draw the components of gravity. Remember that we're not using a traditional x and y axis. Instead, we're rotating it, and we're using an axis. One will be perpendicular to the ramp. The other axis will be parallel to the ramp. And because we rotate it, the components of gravity are tilted as well. Okay. And I've got right here is my same theta shown right to the side. So, mg is the hypotenuse. I can squiggle it out. This component on the y-axis, or the component perpendicular to the ramp, is adjacent. So we use cosine, hypotenuse cosine. This component is opposite theta. So we use mg sine. Okay, we're finished with our pictures, our force diagram. When we write an equation for the y-axis forces, we have to remember the block is not accelerating up off the ramp. It's not accelerating down into the ramp. And so the Fn, the up force, must perfectly cancel mg cos theta pointing down that axis. On that axis, the y-axis, we have balancing of forces. And the reason, again, is because the sum of the tilted y forces is 0. You might prefer to think of this as the sum of the perpendicular forces perpendicular to the ramp is 0. On the x-axis, we cannot balance left and right because they say the block is accelerating along the tilted x-axis. So instead, we have to write down what the net force equals. Oops. And what does the net force equal? Well, there are 3 forces that don't cancel out. The y forces cancel, but you still got Fa, you've still got Fk, and mg sine theta. Fa is positive because it points up. Mg sine theta is negative because it's pointing down the ramp or to the left. Same for Fk, negative because it's pointing to the left. So our equation is this: positive Fa, negative Fk, and negative mg sine theta. For the next one, okay, we always can put Fn and mg. I went ahead and I added friction force because they said it's present. Is there an applied force? Yes, Fa. It's directed down the ramp. So it's something like this. They say the block is accelerating. We have to draw the components of gravity. So they're tilted, tilted y, tilted x. Here is the angle theta in the right triangle. The tilted x component is found with cosine because it's opposite theta. The tilted y is adjacent theta, so we do hypotenuse times sine. Okay. Again, the block, and I can squiggle out the hypotenuse once I'm finished breaking it into its components. The block isn't accelerating off the ramp. It's not accelerating into the ramp. So those forces must perfectly balance. We know that Fn equals mg cos theta. In other words, as we said before, that force perfectly balances the tilted down force. Okay. On the x-axis, there are, okay, so with these 2 forces have canceled, but we still have Fk on the x-axis, Fa, and mg cos theta, the guy pointing to the right. This time, Fa is positive because it points down the ramp, Fk is negative because it's pointing to the left. You know, down. This is to the right. This guy is to the right. Fk is to the left. Mg is to the right, so it's positive. So when we take those forces and add them up, they give us the net force because the y-axis, right, it all canceled out on the y. And so what does that look like? Well, you got Fa is positive. You've got Mg sine theta is positive, but Fk is negative because it points to the left. Number 3. Okay, I drew the friction force, which is always opposite the motion. This block is going up the ramp. Okay, I need to add an applied force, right? There it is. The applied force is directed along the ramp, pointing up it. There it is, Fa. Are we accelerating or constant velocity? Woohoo! We have constant velocity. Let's draw the components of gravity. The one down here is mg sine because it's opposite the angle, theta. And the tilted y component is actually mg cosine because it's adjacent theta. When we balance the up-down forces, just like before, we get this. But look at what we've got. Constant velocity. So we can balance left and right as well. There are two forces pointing left, Fk and this mg sine theta. One force points right. And so what we have when we balance the lefts with the right, we have this. That's the force pointing right, those point left. Remember that when we balance left and right, we make everything absolute valued. That's why it's all positive in this equation. Okay, number 4. The block is going down, constant velocity again. So we can use these two equations. There is no applied force. There is friction, so I drew that in. So my picture is done. All I have to do is add the components of gravity, and I have to label them because it says make a labeled diagram. The component down here on the x-axis, the tilted x-axis, is opposite theta, so we do sine. The component up here on the tilted y-axis is adjacent theta, so we do cosine. When we balance forces on the y-axis, just like we've already seen, we have normal force balancing the tilted y component of gravity. When we balance on the x-axis, because it is constant velocity, the only leftward force is Fk. The only rightward force is mg sine theta. So those two things, they balance each other. Number 5. There's no friction, they say. There's no applied force. So all we have is the normal force and mg. Whoops, my... what happened? This is not covered. So on the y-axis, well, I can't really look at the y-axis till I draw components of gravity. So let me draw, there's the y component of gravity, the tilted y. Here's the tilted x component. There's theta. The y component, as always, is mg sine theta. Whoops, cosine, because it's adjacent the angle. And in all these ramp problems, the tilted x component is mg sine theta. So when we balance up and down, just like we've done already so many times, we get Fn is mg cosine theta. So these forces cancel, these two. The cancellation station. On the x-axis, this is the only force that remains. There's no Fa, there's no Fk, so our net force is mg sine theta. Number 6, I drew Fn and mg because those are in every single problem. Is there an applied force? Yes, and it's directed up the ramp, up along the ramp like this. It's probably too long. They say there is no friction, so I'm done. All I have to do next is add components to the gravity force. Make sure your tilted x component is actually tilted. And here is theta right there. The tilted y component is adjacent theta, so we use cosine. This tilted x component is hypotenuse. Mg is the hypotenuse of this triangle. And we use sine because this tilted x component is opposite theta. Okay, again, if we balance left and right, because it is constant velocity, so we can balance left and right, we get the only left force is mg sine theta, and the only arrow pointing to the right in this picture is Fa. So they would perfectly balance. If we balance the y-axis forces, just as before, the up force tilted up, Fn, balances tilted down. Number 7. Looks like I didn't get to this one to draw. We've got mg pulling down. Fn is always there as well. It's constant velocity. Friction is present. So if the thing is going this way, friction is opposite. Friction is always opposite the direction of motion for kinetic friction. Let's see, constant velocity, an applied force is there directed down the ramp. So the applied force is like this. And you know what? I better draw my friction arrow a little bit longer if this is going to be, or sorry, a little, longer. You'll see why in just a second. I have to draw the components of gravity. And here is theta. The tilted y component of gravity is hypotenuse cosine because it's adjacent to theta. This tilted x component is hypotenuse sine theta. Okay, constant velocity now. When I balance up and down, just like we've been doing the whole time, is there an equation here to reveal? No. When I balance up, pointing up along the tilted y-axis is Fn. Pointing down on the tilted y-axis is mg cos theta. When I balance left and right, because after all, velocity is constant, pointing leftward is just Fk. Pointing to the right is, we have two things. Fa points to the right, and mg sine theta points to the right. So let me add them both on the right side. Okay. For every scenario, write an equation for the kinetic friction force. Well, I know Fk is mu times the normal force, but they're asking me to use mg and theta. So what's my actual answer? Well, the normal force in every single problem was mg cosine theta. That's my final answer.